topic we're going to explain is uniform circular motion. And so uniform circular motion is an object traveling in a circular motion at a constant velocity. So for this I have a demonstration with a rope tied to a key. But before I show the demonstration, I want to explain a few relevant terms such as centrifugal force, centripetal force, and centripetal acceleration. Centrifugal force and centripetal force are basically equal and opposite, as said by Newton's third law. So centripetal force is the inward force that keeps the object in a circle, and then centrifugal force is the outward force that is felt by the key, because the key is in a rotating frame of reference and it feels the centrifugal force as if it's moving outwards. And both have the same formula, F subscript C equals mv squared over r. And then there's centripetal acceleration, which is the acceleration the acceleration vector always points towards the center of the circle. So that's the centripetal acceleration. The formula for centripetal acceleration is AC equals v squared over r. So this is the demonstration. So rope tied to a key. So as I move it in a circle, the centripetal acceleration vector, it points towards the middle. The centrifugal force is felt by the key outwards. Centripetal force is the inward force that goes inwards. And then the motion, which is the velocity vector, that is tangent to the circle. So it's tangent to the circular motion. That's the velocity vector. So I'll be making calculations in the next clip. But I want to make a connection to another course, which is phys ed. Phys ed, there's a sport called hammer throw, where there's a big hammer and the player has to rotate the hammer. Just like I rotate the key, you have to rotate the hammer in a circular motion until you get enough speed, and when you release it, the hammer goes and lands at a certain spot. So the farther the hammer is, you win. So there's a number of players that play. So you need enough speed, moving in a circular motion for the hammer, and then you release it. And I'll be making calculations in the next clip. So now we'll be making calculations with centripetal acceleration and centripetal force. So the formula is for centripetal acceleration is v squared over r, and centrifugal force is mv squared over r. So let's say the mass of the key is 0.005 kg, and let's say the radius was 5 meters. And let's say the velocity we were moving the key was at let's say 15 meters per second. Now with that we can find the answer to both formulas. So AC would be 15 squared over 5, and that would be 45 meters per second squared. So that's the centripetal acceleration, the vector that points towards the middle, and then the centripetal force with Fc equals 0.005 kg times 15 squared divided by 5 equals 15 squared times 0.005 divided by 5. So 0.23 newtons. So centripetal acceleration is 45 meters per second squared, and the centrifugal force and the centripetal force, which are equal and opposite, is 0.23 newtons. My second topic is going to be elastic collision. So momentum and how momentum is conserved. So I have a small demonstration here that I'll show later on, but before that I want to explain momentum, elastic collision, and inelastic collision. Momentum is the quantity of motion of a moving body, which is defined as the product of its mass and velocity. P equals mv, that's the formula. So where P is momentum, m is mass, and v is velocity of the body. So elastic collision is a collision of two bodies where momentum is conserved and kinetic energy is also conserved. Inelastic collision is a collision where momentum is conserved and kinetic energy is not conserved. So kinetic energy is lost due to internal friction. So nonetheless, momentum is always conserved. So when I say momentum is conserved, I mean the momentum lost by one body is going to be gained by another body, and the formula is m1 v1i plus m2 v2i, which is momentum of the body initially equals m1 equals m1 v1f plus m2 v2f, which is the momentum of the final momentum of the two bodies. So over here I'm going to be showing an inelastic collision. So one car is going to be at rest, initially at rest, and one car is going to be moving at an initial velocity. So as this car is moving, so let's do that again. So as this car is moving, both are going to have a final velocity. Their momentum is conserved, and so is kinetic energy because it's an elastic collision. So let me do that again. The car's at rest, this car's moving at velocity, and then as they move on, they're both gonna be moving at some velocity, and that's what I'm gonna figure out in another calculation, in another clip. So I wanna also make this connection to phys ed, and this is gonna be tackle football, which is taught in the higher grades of high school. So that is where this is gonna be an example of inelastic collision with tackle football, where one person is running with the football, and one person is gonna be running after him to tackle him. So when he reaches him, he's gonna tackle him, and then they're initially both traveling at a velocity, but then when the guy tackles him, they're both gonna be traveling at the same velocity. So when they're traveling at the same velocity, that means momentum is conserved, but kinetic energy is not. It's an example of inelastic collision. So that's a phys ed example, and I'll be doing my calculation to find the final velocity of this example, which is elastic collision. Okay, so I'm going to be using two equations to find the final velocity of both the bodies. So the final velocity of the first body is m1 minus m2 over m1 plus m2 times v1 initial. Then the final velocity of the second body is 2 times m1 over m1 plus m2 times v1 initial. Now these two equations only apply under two conditions, where it's an elastic collision and where the second body has to have an initial velocity of 0. So if the second body is moving at a velocity, then these equations will not work. The second body has to be at an initial velocity of 0, so its momentum has to be 0. Okay, so here's are the masses. So let's say a mass of the first car is 0.015 kg, and the mass of the second car is 0.01 kg. And let's say v1 initial equals let's say 20 meters per second. Now we don't need to write v1f because we know it's going to be we don't have to write v2 initial because we know it's going to be 0 meters per second because the second body is at rest. So if you use our equations, you have to apply all this to find the final velocity of the first body. So let's do that. Let's do it. So 0.0115 minus 0.01 over 0.015 plus 0.01, okay, times the v1 initial, which is 20 meters per second. That's the equation. So okay, so it's 4. So the final velocity of the first body equals 4 meters per second. That's the, and now v2f equals, let's apply that into our equation. Let's sub everything in. So that's going to be 2 times the first mass, which is 0.015 times m1 plus m2, 0.015 plus 0.01 times v1 initial, which is 20 meters per second, which is 24 meters per second. v1 24 meters per second. Okay, so that's our final velocity, and it makes sense because because momentum is conserved in an elastic collision. So since the initial velocity of the second body was 0, it'll have 24 meters per second, and since this was 20 meters per second, it will lose all of its momentum and it will have a less speed, which is 4 meters per second, which is v1f. So these two answers do make sense. The polarization of light off non-metallic surfaces. So I have a small clip that I want to show for a demonstration that shows how fishermen see water and fishes using polarized and then non-polarized sunglasses. So that's going to be for later, but first I want to give a small explanation. So light from the sun comes unpolarized, so it vibrates in many planes. But when it hits something that is non-metallic, like the river in this case, it becomes polarized in a way that is parallel to the surface of the water. And then the reason why fishermen wear sunglasses is because the sunglasses are polarized in a way that is the polarized sunglasses are oriented in such a way that does not correspond to the orientation of the polarized light. So basically, both planes do not match. And this way, since the planes do not match, the planes do not match, the glare is blocked out for the fishermen. So I have a few terms I want to explain, such as electromagnetic wave, electromagnetic spectrum, and polarization. Electromagnetic waves are basically waves that have oscillating magnetic and the electromagnetic waves are waves that have oscillating magnetic and electric fields, and they vibrate with a velocity that was always going to be the same. Velocity will be 3.0 times 10 to the 8 meters per second. In this way, this is going to be true for all light waves. And then the electromagnetic spectrum. Electromagnetic spectrum is a series of electromagnetic radiation that showcases certain wavelengths, certain frequencies, and certain energy of waves. On one end, there's going to be, for example, radio waves that has a high wavelength, a short frequency, and basically low energy. And radio waves come from stuff such as radio towers. And then there's another end, there's stuff like ultraviolet rays that have low frequencies, they have high frequencies, low wavelengths, and therefore high energy. And they come from stuff like the sun. And then there's one last term, polarization. Polarization refers to the number of orientation, the vibrations of a light wave. So, like I said before, from the sun, light waves come unpolarized, so they vibrate in many different planes. But when they become polarized, they vibrate in a single plane. So, yeah, you can also use a polarizer to polarize something. And now, speaking of ultraviolet rays, I wanted to connect it to biology, because ultraviolet rays do come from the sun, and from the sun, ultraviolet rays, they're essential because they help in activating and promoting vitamin D, and vitamin D does help in absorbing calcium, and calcium, in return, it helps in maintaining strong bones and strong teeth, and therefore it prevents osteoporosis. So it prevents weak bones and weak teeth and stuff in the body, and also too much ultraviolet radiation can also cause cancer. So that's kind of biology, and now let's get to the demonstration. Alright, so say we want to find the ultraviolet electromagnetic waves in general have the same formula for velocity. Velocity equals frequency times wavelength, and we always know that the velocity of light waves will be 3.0 times 10 to the 8 meters per second, and it's never going to change. That's going to be the speed of light in a vacuum in space. Then let's say we want to find the frequency of ultraviolet rays. So the ultraviolet rays wavelength would be something around 350 nanometers, which would be like 3.5 times 10 to the negative 7 meters. And for frequency, just isolate for frequency. Frequency equals 3.0 times 10 to the 8 meters per second divided by 3.5 times 10 to the negative 7 meters. Now the frequency will equal, let me get my calculator, 3.0 times 10 to the 8 divided by 3.5 times 10 to the negative 7. 8.6 times 10 to the 14 hertz. And that's going to be the frequency of ultraviolet rays.